So welcome back. We're in lesson 2. We're reviewing graphical characteristics, but the only distinction is we're applying those characteristics to rationals. So if I was going to, let's say, draw a horizontal line. Horizontal lines are created at y values. All the y values are the same. So when y values are the same, you're typically creating a straight line when you're talking about 2 dimensions at a y value. The y value we have here goes through the y-axis at 3. So this equation is y equals 3. The slope here is 0. Okay? Now, vertical lines are where all the x values are the same. We create this line, all x values are the same. So here, where x equals 3, this is the equation, x equals 3, my slope is undefined. All right? And what we're going to be doing in this unit is exploring asymptotes, and those are vertical asymptotes where they have the equation of x equals a number, and horizontal asymptotes where they have the equation y equals a number. So here, all of these x values, every single x value is 3. But for my y values, they change. So x equals 3 here. Down here, all of my y values are at the same level. So y equals -3. Okay? Moving on. Now, an asymptote is a line that continually approaches a given curve but does not meet it at any finite distance. That's very formal language. So a curve, if you look at the map of these graphs, you have dashed lines. The dashed lines aren't really a part of the graph itself. It just shows you where asymptotes are located. Algebraically, asymptotes are in the bottom of your equation. They're the opposites of the factors in the bottom of your equation. Okay? So vertical asymptotes are imaginary vertical lines where a curve converges with the equation x equals a number. And here, that number happens to be 3. This is x equals 3. This is a vertical asymptote. Vertical asymptotes right here. Over here in this equation, my vertical asymptote, I have x equals -3, and I have x equals 2. So what's happening is the curve is approaching 3 in the first one, and then in the second one the curve is approaching -3, but it never quite touches -3, never goes over -3. It's approaching x equals 2 or 2, but it never touches those. Algebraically, if you look at your factors, they're the opposite. They're the opposites of these equations that you see on your paper. Now, horizontal asymptotes work similarly. We won't talk about really how to look at them algebraically just yet, but you can see where the curve is approaching. It's approaching this place horizontally, right? But it never quite touches. So here, it's at y equals 1. Over here, it's at y equals 0. All right? Now, when we write these asymptotes, we have, so y equals 1 over here, y equals 0 over here, and then for our vertical asymptotes, we have one equation here, x equals 3, but over here we have x equals -3 and x equals +2. All right. Just doing the math. If I wanted to do the math, I would take that factor in the bottom, set it equal to 0, and solve. And I get x equals 3 algebraically. All right? Same thing with the second object, but we've done what we need to do. Now, the next part, we're going to graph the rational. So my graphing calculator, my screen graphing calculator is currently not working. But what we do is we go to y equals, we clear out any equations that are there, and we press 1 over x, and then we go to the table, and we get our values. So we skip decimals typically, but what you'll notice is we have, I'm just going to put some decimals though. So I have -3, -0.33, -2, -0.5, -1, 1, 0, error, 1, 1, and 2.5. So after that, you can press trace to look at the actual object. Okay? So what you'll notice is there's a error at 0. This is a special place. This kind of indicates that there's a asymptote of some kind there, but the object doesn't touch it. Now, on the left, I'm going to go left 3 down 0.33. So left 3 down 0.33. Left 2 down 0.5. Left 1 down 1. Oh, did I do it right? Let's make sure I did that correctly. Yes. So this should be -1. My bad. Okay. And then the points get ever closer and closer to this y-axis. So on the left, I have this curve, and it's getting closer and closer to y = 0. If I keep going towards the right, my y values go to -infinity. Okay? So up top, my y values are going towards this asymptote 0. So I'm just going to graph right there. That's my asymptote. That's y = 0. So as my x values move towards -infinity, as they go towards the left, y values go to 0. Or we also call this f of x. They go to 0. They go to 0. Okay? As we move to the right, those y values go to -infinity. So I'm going to bring this down a little bit so we can look at that. All right? Now, let's continue graphing. So I don't have any values at 0, but I do at 1, 1. I do at 2.5. And what's happening is it's like it just skipped over 0, and it's coming all the way from positive infinity for those y values. And then it's going back down, and it wants to hit that x-axis, but it never quite does. And that suggests that I have a horizontal asymptote at y = 0. Now, because it never hits the y-axis, this suggests I have a horizontal asymptote, a vertical asymptote at x = 0. And if I look at my equation at the bottom, my factor at the bottom of this equation, it's x, and x = 0. That's my asymptote. Okay? So asymptotes, we pretty much have that mapped out. But excluded values here will be real numbers for which a rational function is not defined. So any numbers, any x values where rationals are not defined. So x = 0, this rational never hits 0. It never hits 0. My asymptote, so my vertical asymptote, is x = 0. My horizontal asymptote is y = 0. My domain. So I come from -infinity over here. I skip over 0. and I keep going to positive infinity. So what does that look like algebraically? Well, from negative infinity, it's a parentheses around that, to 0, and we always use parentheses when we're speaking in terms of skipped or excluded values, and then 0 to positive infinity. Now with your y values, you're coming from negative infinity, looks like you skip over 0 here, and then you keep going to positive infinity. So from negative infinity, comma, 0, we keep going to positive infinity. Skip over 0. This kind of implies a skip over 0. All right. Now, increasing intervals. So I'm going to highlight intervals where we're increasing. So, y values are never increasing as we move to the right. They're never increasing as we move to the right. But, so for y values increasing as we move to the right, they don't exist. Do not exist. All right. Now, y values as we move to the right are decreasing. So here they're decreasing. So from this interval, from negative infinity over to 0, from negative infinity over to 0, y values are decreasing. From 0 to positive infinity, y values are decreasing. So it's the same as my domain. So from negative infinity to 0, 0 to positive infinity. Now x-intercepts, does it cross the x-axis? X-intercepts do not exist for the parent function of rationals. This is your parent function of all rationals. All right. Y-intercepts doesn't cross the y-axis, so these do not exist. Now, as I move to the right, as I move towards the right, positive infinity implies the right, my y values are moving down towards 0. As I move to the left, y values are increasing towards 0. Okay? So we're going to practice that a little bit. So no worries. But moving on. Now we're going to do graphical characteristics of this rational. So things I can already tell from the graph. I know I have a vertical asymptote at x equals -1. I have a horizontal asymptote at y equals, let's see, 1, -2, -3, -4.5. Okay? Excluded values here would be my asymptote. Now, what are we graphing? We're graphing the function family of rationals. The parent function of rationals is y equals 1 over x. That's the parent function. Now, asymptotes, we have x equals -1 and y equals -4.5. My domain, coming from the left, I'm coming from negative infinity. I stop at this point, -1, and then I keep going to positive infinity. So my domain looks like this: negative infinity, stop at -1, so there's a parentheses there, put a little u, -1 to positive infinity. My range, starting at negative infinity, I stop right here at -4.5, and I move up to positive infinity. So you can see your asymptotes and your domain and range are very connected. So negative infinity, comma, -4.5, u, -4.5, infinity, and put parentheses there. Okay? Now, increasing, decreasing. So values are always decreasing as we move to the right. Y values are always decreasing as we move to the right. And if I keep going to the right, even if I skip over that x value of -1, we're still decreasing. These these are this is exactly your domain, so it's never increasing. So an increasing interval does not exist. No y values are ever increasing as I move to the right. But the decreasing interval is the same as the domain. It's the same as the domain. Now, x-intercepts, let's erase some of this information I have here. I have an x-intercept right here, and it looks like x equals -0.7, right? But when we're writing x-intercepts, we write the coordinate, -0.7, comma, 0. Y-intercepts, right here at 0, comma, -2. So I write 0, comma, -2. My 0 is the x value in the x-intercept, so -0.7. The end behavior of this particular function is asking you what happens as we move to the right. Well, as we move to the right, we're moving down to -4.5. Y is moving down to -4.5. What about as we move to -infinity or to the left? Well, as we move to the left, all right. So guys, before we get started on graphical characteristics of this rational, please do me a favor and let's make a correction here. Now, our horizontal asymptote is a little bit off because if you look at the curve, it goes right through the asymptote. So our asymptote is actually right here. The horizontal asymptote is right here. And we're just going to make a slight correction. And we're going to write so we know y equals -3 here. And up here, our vertical asymptote is x equals -1. And it's not incorrect. But let's go through this. So our function family is the family of rationals. This graph belongs to the family of rationals. The parent function is y equals 1 over x. This is my parent function. Okay. Now, my asymptotes, we already identified those. We have x equals -1 and y equals -3. The domain, I'm coming from -infinity. I stop at -1, and I keep going to positive infinity. So this curve goes to -infinity, approaches -1, never touches it, skips over it, comes back down, and it's going to positive infinity. So from -infinity to -1, union, -1, back, and then to positive infinity. My domain, coming from the bottom, is coming from -infinity, stops at -3, goes up to positive infinity, or it skips over -3. So from -infinity, goes up to -3, skips over it, starts back up at -3, and continues on to positive infinity. Now, is this function ever, are the y values ever increasing as we move to the right? Well, here they're going down, and when I start back up again, they're still going downwards. So no, these are never increasing. So an increasing interval doesn't exist. However, what about decreasing? Well, looking at the yellow, the decreasing interval, if we're looking at our x values, it's the exact same as our domain. So -infinity to -1, union -1 to positive infinity. Now, x-intercepts. I have an x-intercept here. It's at -0.7, comma 0. So -0.7, comma 0. And my 0 is x equals -0.7. Now, my y-intercept is down here at 0, -2. So I'm going to write 0, comma, -2. The end behavior, it's going, if I'm going towards the right, I'm going towards the right. So this implies I'm going towards the right. As I go towards the right, my y values go down to that horizontal asymptote. They are going towards -2. They never, I'm sorry, -3. They never quite reach -3, but they're converging towards -3. That is not negative infinity. As we move towards the left, they're going up towards -3. So that's what that implies. When we go towards negative infinity, we move towards the left. So they're going up towards -3. Okay? Now next, we're going to look at what we call holes. Holes are missing points from the graph of a rational function. Holes occur where a given x value makes both the numerator and denominator 0. So you'll recall, holes are going to be easy to identify as we move forward. Okay? So what I'm asking you to do here is identify the holes, vertical asymptotes, horizontal asymptotes, domain and range, to see the connection between all of these key graphical characteristics. So the first graph I give you is a straight line. It definitely has a hole. It has a hole right here at right 2 up 3, so at 2, 3. The hole is at 2, 3. Does it have a vertical asymptote? Does it have this place that it's approaching but never touches? There does not exist. Does not exist either. The horizontal asymptote does not exist. But my domain, it's coming from negative infinity, stops at 2, and then continues on to positive infinity. So from negative infinity, stopping at 2, and it's a parentheses, because it never touches 2, union 2 to positive infinity, close parentheses. Your range, on the other hand, it does come from the bottom, so from negative infinity up to 3 on to positive infinity. So from negative infinity up to 3 on to positive infinity. All right? And that's all of the graphical characteristics we're going to go over for that particular function. Now, we do have asymptotes. But let's get our hole first. Our hole is right here at, looks like 1, 0, 1. Looks like 0, 1. That's our hole. So it's going to be a part of our domain. All right? Now, our vertical asymptote is at x equals -0.5. So x equals -0.5. Our horizontal asymptote is at y equals 2. Y equals 2. So let's look at our domain here. Let's look at our domain. Let's all right, so our domain, it's coming from negative infinity. It stops at -0.5, right? And then it continues on until it gets to 0, and then it starts back up at positive infinity. So I'm coming over from negative infinity, stop at -0.5, continue back to 0, then starts up again at 0 and goes to positive infinity. So this is what our domain does. It says negative infinity, stops off at -0.5 for that vertical asymptote. All right. Um, there's a break there, so we put a union. Then from the vertical asymptote over to the hole. Okay, so VA to the hole. And then from the hole at 0 over to positive infinity. So we have 3 different intervals where this graph hits the x values. For your y values, for your range, we start coming from negative infinity, we go up to 1, and then we go from 1 to 2, and then we continue on to positive infinity. So we have 3 breaks there too. So we start here at negative infinity, stop at 1, from 1 to 2, and then from 2 to positive infinity. So maybe it'll be a little easier as we do the next one. So here for the next one, our hole is at 3, comma 0.5. And I love that they provided a graph here because you can see also algebraically our holes are the things that cancel out. All right. Now vertical asymptote, it's what's left over. It's going to be x equals 1, and it's pointed out right here. Our horizontal asymptote is y equals 0, and we'll figure out how to see that algebraically soon. So our domain technically should be from negative infinity to 1, and then 1 to 3, and then 3 to infinity. But let's just make sure. So negative infinity over to 1 at our vertical asymptote, then it stops off at 3, and then on to positive infinity. So from negative infinity over to 1, from 1, oh, put a little u there. Just put a little u there. Don't want to mess it up there. So union 1 over to 3, and then union 3 on to positive infinity. Our range comes from negative infinity, stops off at 0, continues to 0.5, and then goes on to infinity. So for our range, we're going to write negative infinity, stopping at 0, continuing on from 0 to up to 0.5, up to the y value 0.5, union, and then from 0.5 on to infinity. Okay, moving on, next page. Now, what does this look like algebraically? So there's these are called discontinuities. These places, these breaks in our intervals, these breaks graphically where the graph, the object stops, it doesn't hit. These are called discontinuities. So there's a couple of different types. So holes will not show up on your screen. You have to factor your numerator and your denominator in your rational. You have to cancel out any factors that appear in both the numerator and the denominator. You set each factor that was canceled to equal 0 and solve for x. For algebra 2, you will not need to, but you can use the value for x to substitute and simplify to find the value of y. So I'm looking for an expression that I can cancel from the top and the bottom. In this expression here, I'm going to highlight it. This expression, hold on a second. Okay. All right, so this expression that's the same would be x minus 5 and x minus 5. So that's your whole. It's the expression that's the same at the top and the bottom. And what happens is you cancel it out, and it causes a big hole. So we have x minus 5 equals 0. We solve for this x, and we find out x equals 5. All right? So we have a hole at 5, and now we need to find the y value. So f of 5 equals what's left, 3 times 5 plus 1 over 5 plus 2, whatever's left when you cancel it out. 3 times 6 over 7 equals 18 over 7. So here is my y value, 18 over 7. Okay? But you have to take away the x minus 5 first to find that hole, to find the y value here. This is x, this is y. There's my hole. Okay? Now, what about the other these other values here? All right? So for the vertical asymptote, this is what's left in the simplified version. So where are we at with the equation? After it's simplified, we have f of x equals 3 parentheses x plus 1 over x plus 2. So my vertical asymptote is down here in the bottom. It's that bottom factor that affects that asymptote. So x plus 2 equals 0. We subtract 2 on both sides, and x equals negative 2. So here I have a vertical asymptote at x equals negative 2. So now horizontal asymptotes, how do I gather what those are? We're going to use a new equation to identify horizontal asymptotes, but had I used the last equation, I would find that I have a horizontal asymptote at 3. But we're not going to use this last equation. My new equation is f of x equals 5x plus 2 divided by 4x plus 1. So what we're looking at says if the numerator and denominator have the same degree, so the x value, we're looking at our x's, and if these x values are the same type of x's, so I have x to the 1 power at the top, so this is a first degree polynomial, and x to the 1 power at the bottom, this is a first degree polynomial. If they are the same, then we take a ratio of their leading coefficients. We take a ratio of those leading coefficients, or the numbers in front of those x's. This ratio here is y equals 5 over 4. And it only applies when the x's have the same degree. The biggest x's have the same degree. Now let's say on the bottom, in the denominator, there's a higher degree than the numerator. Then it's automatically that the asymptote is at y equals 0. So here, this is the x-axis. It's automatic that the asymptote is at the x-axis. So here, look at your leading coefficient at the top. It's negative 3x. This power is to the 1 power. At the bottom, it's x to the 3rd. So I have a bigger degree polynomial at the bottom, so it's automatically y equals 0. Don't stress over horizontal asymptotes. Now, what about when there's a higher degree in the top? There's a higher degree in the numerator. If there is no real number x that makes the denominator equal 0, if there is no real number x that makes the denominator equal 0, okay, only. And if the numerator has a higher degree than the denominator. So here the degree is higher than the bottom, and here the degree is higher than x squared. So here the horizontal asymptote doesn't exist. One does not exist. Okay? So algebraically, we should be able to figure these things out. So let's move on to identifying these asymptotes algebraically. So first, I know that there's a hole. There's a hole at this cancel factor. There's a hole at x equals -2. I know that there's a vertical asymptote at this opposite here at x equals 3. And then with the simplified fraction, I have x minus 1 over x minus 3. The degree is the same on the top, and then the degree of the polynomial is the same on the bottom. So y equals, put a 1 in front for the coefficients, 1 over 1, or it just equals 1, is my horizontal asymptote. So I'm going to draw these things on the graph. I'm going to show my vertical asymptote. It's not asking you to do that, but it's good practice. So I have x equals 3 here. Horizontal asymptote, I have y equals 1, and you can see it clearly now coming together. And then my hole, I have a hole at -2, so I'm going to go find -2, go up to the graph, and there's a hole there at where x equals -2. Okay? Looking at the next one, there are no holes, so holes do not exist. There's nothing I can cancel there. I do have a vertical asymptote. Let's see, 2x plus 1 equals 0. So I subtract 1 on both sides, get 2x equals -1, divide both sides by 2, and x equals -1/2. There is my vertical asymptote. I'm going to just go ahead and draw it here. A little bit hard to draw. So x equals -1/2, or x equals -0.5. My horizontal asymptote, these are these coefficients here. These leading coefficients of these x's would imply a horizontal asymptote. The degrees of the polynomial are the same on the bottom, so y equals 3 over 2. Y equals literally 1.5. That's my horizontal asymptote. Okay? Looking at example number 3, it's factored for you. So I do have canceled values, and I'm left with 1 over x plus 2. All right? So the value of my hole is x equals +2. Vertical asymptote is x equals -2. Now, looking at my equation, what's my horizontal asymptote? Well, there's a 0-degree polynomial up top and a 1-degree polynomial on the bottom, so that implies that there's a bigger denominator in terms of degree at the bottom. That implies my horizontal asymptote is automatically y equals 0. Now, example number 4, there are no holes, but there are excluded values. This includes my vertical asymptote, which is at x equals 2. So x equals 2 is a vertical asymptote. My horizontal asymptote, these are the same degree polynomials, so 1 over 1, or y equals 1, is my horizontal asymptote. My domain comes from -infinity over to my vertical asymptote, so maybe want to make a note, domain -infinity to the vertical asymptote, then it starts back up to vertical asymptote over to +infinity. So -infinity to +2, then union 2 to +infinity. Your range comes from -infinity, goes up to your horizontal asymptote, and then continues on to +infinity. So from -infinity up to 1, union 1 to +infinity. Intervals of increasing or decreasing, well, if you look at the graph, it's either increasing, the y values are either increasing as you move to the right, or they are decreasing as you move to the right. And like I said, I don't have my on-screen calculator is currently not working, so you'll definitely have to put those in your graph to look at it. And looking at it, it looks like y values are decreasing. So an increasing interval does not exist, and it's just going to be the same as your domain for decreasing. Okay? Now, zeros for this graph would be anything that makes where it crosses the x-axis, the place where it crosses the x-axis, so it makes y values equal 0. So that would be where x equals -2. So I have -2, 0, right? So I'm looking at the numerator to determine that. Y-intercepts, this is where y equals 0. X equals 0. So I get 0, -1. If you wanted your y-intercept, you could just plug in 0 here. And I get 2 over -2. This simplifies to -1. So my y-intercept is 0, -1. The end behavior, as it moves to the right, goes to your horizontal asymptote, so it goes to 1. As you move towards the left, it goes to 1 towards your horizontal asymptote. Excluded values here. Look at the bottom. Anything that doesn't cancel out. X equals 2. The opposite of anything that doesn't cancel out. X equals -7. Vertical asymptotes. X equals 2 and x equals -7. Horizontal asymptotes, these are the same here. These are the same degree. So my horizontal asymptote is y equals 1, -1, -1. My domain is -infinity to my x, what x equals in an excluded value. So from -infinity to 2, union 2, I made a mistake. The smaller number comes first, from -infinity to -7, parentheses, union, -7 to 2, union, and then 2 to positive infinity. My range from -infinity over to my horizontal asymptote, so to -1, union, -1 to positive infinity. Intervals of increase, same as domain. So from negative, it doesn't exist. It does. Wait, let's make sure. Let's make sure here. Actually, it does exist. So let's put our function into the graphing calculator. So intervals of increasing occur from, looks like around -3 to positive first 0, 2. All right, and that's the only interval of increasing. intervals of decreasing, I'm coming from negative infinity over to negative infinity over to negative 7, union negative 7 over to negative 3, union, and then skipping this interval, negative 3 to 2, from 2 to positive infinity. My zeros here, I have a 0 at negative 4 and a 0 at negative 2. So zeros, x equals negative 4, and then a 0 at x equals negative 2. So I got this from the top here, and x-intercepts, negative 4 comma 0, and then negative 2 comma 0. Y-intercepts, this is where y equals 0. We're going to have 4 times 2, 8 over negative 14, or 0, comma, when we plug 0 in, we get 8 over negative 8 over negative 14, and we get, simplifying that, we get a positive number. We get 4 over 7. 4 over 7. In behavior, it's going up to this this horizontal asymptote to negative 1 and to negative 1. All right. Pretty much the last thing we're going to cover is transformations of these functions. So these functions can reflect. They can reflect. So if I were going to look at 1 over x, and then I changed it from okay. So this is what I want you to do. So one of the things that's not included is reflections. Reflections, all right? So let's say I have my function. If I have a parentheses negative x minus h, plus or minus h, who cares? But the x is negative on the bottom, it's going to reflect over the x-axis. So reflects over x-axis. Okay? But let's say I have a negative on the other side, then okay, so let's say I have that. So if it's inside on the bottom, it's reflecting over the y-axis. If it's outside, negative a, x plus h, but not on the bottom, reflects the negative. So it reflects over the x-axis. Okay? Now, keeping that in mind, if the number is greater than 1, there's a vertical stretch a units. If it's less than 1, vertical shrink a units. Shifts right for negative h, shifts left for positive h, shifts left, down for negative k, shifts up for positive k. So I am shifting left 2 units here. So I shift left. That's my transformation. On the next one, there's a negative outside, so this reflects over the x-axis. Okay. Next, we shift up 3. Next, you vertically stretch 2. Down below, we shift left 50. You shift down 32 units. Next, we reflect over x-axis. Okay. Then you shift right 34 units. And you shift up 19 units. Okay? And that's all I have for you today. The next lesson is lesson 3 on multiplying and dividing polynomials. Have a good day, guys.